Okay, there's the screen. Okay, there's little me. Okay, there's a chat window for people's ideas to come through that way. There's a little participants window. It is a quiet morning here in statistics too. Some of us are here. Is it just because it's early? Is it just because it's early? I'm guessing it's because it's early. Next quarter, I'm scheduled to teach statistics one remotely. I think at 8 a.m. on Tuesdays and Thursdays. 8 a.m.
On that one, everyone can literally just wake up at 8, pull out their phone and
Oh,
get into class.
I have to at least go downstairs from where I sleep.
Right.
8 a.m. It's not going to be as fun of a quarter next quarter for me. Well, in any case, let's give it a minute more. Oh, hey, welcome, Quincy. Welcome, welcome. Let's give it about a minute more. Relax, settle in. Let's check out the plan. Hopefully, we'll get a couple more people. I seem to remember last week I was pretty sick. We had like a short class, but we did discuss the scheduled section of our textbook. That was the third one in chapter 7. And our plan for the day, if I'm not wrong, is to just talk about ANOVA, a fancy thing. And to remind you, did you write up your interview summary? It's due today officially. Oh, I hope you did. Uh, and then a bonus reminder, I have made zero progress grading since I got sick last week. So though today I believe is the day where I will go to the cubicle after this class and do my best to focus on opening up the giant digital box of midterms from all 3 classes and all your recent homework and start to score things in some vaguely random order so that I'm not like, it wouldn't be fair to try to get things done in the order they were done, because that would just, just the lucky class would get way more attention that did things first, right? So I'll just kind of randomly and energy wise work through things and keep updating you all as progress gets made. So please apologize for just a bummer. If I had not gotten sick on top of the weather, we'd probably be in a different spot with that. But we'll never know. Sickly me. Also, my co-parent got sick. That wrecked my whole weekend. The dream was to catch up on the weekend, but my co-parent was sicker than I was, and so I needed to do a ton of extra parenting and helping them out. So, all right, but let's talk about well, wait, any questions from anybody? I mean, there's only a few of us here in this moment, but does anybody have any questions about recent work? Anything on your mind, stats class? Hey, a homework question. I love those. Yes, I would please talk about the chicken diet and weight question in section 7.3. I'd be happy to. That's a great question. Let's talk about it. I will go open up the online book. That one. I'll go to the third section of chapter 7. And I'm just going to type find chicken. There it is. Okay, cool. Okay, and then what I'm gonna do is, well, let's read it, and then as we get into it, you know, we'll probably take, if I have to type stuff up, we'll take it over to the class notes to save it for everybody. Okay, I'm guessing not everybody started this problem. That was like the most recent section we discussed, so let's just read it together. Chicken farming is an exploitive, ugly, dangerous, multi-billion-dollar industry in which human beings and animals are horrifically harmed. I was listening to the news on the way to school, so I'm a little grouchy. And and any methods that increase the growth rate of young chicks can reduce consumer costs. That ever happen? You ever notice the price of anything ever go down during your life, like drastically? I've never noticed. Maybe VCRs got less expensive when I was a child for a little while there. Could reduce consumer costs, though, while increasing company profits. Economics 101. Possibly by millions of dollars. Trust me, company profits have increased by millions of dollars. That is true. Costs have not gone down for consumers. An experiment was conducted to measure and compare the effectiveness of various feed supplements on the growth rate of chickens. Okay, so if they force feed tiny, fragile creatures different kinds of food, will it fatten them up for slaughter better? Newly hatched chicks were randomly allocated into 6 groups, and each group was given a different feed supplement. Below are some summary statistics from this data set, along with box plots showing the distribution of weights by feed type. Before I go on, I'm going to say I'm switching my mental picture of what's happening from the horrific real-life factory farming images I started with to more like a Disney movie of some little cartoon chicks happily bouncing around in a beautifully painted fantasy world where there's one little group of little chicks who are eating casein, another little cute group of like maybe they're pink ones who are all eating horse bean, a little group of lavender colored ones who are eating linseed. It's like an Easter magic universe of happy joy. Uh, and of course, my favorite little group are eating meat meal. I mean, who doesn't love a plate of meat meal in the morning? Soybean, sunflower. Okay, that's the setup. And you can see the box plots there. Uh, there's a little bit of missing information. Uh, there's a lot. We're missing a lot of information here. They didn't tell us about how many chicks are in each group, or I mean, we have graphical statistics. Oh, it's on the PDF. Oh, I'm missing information because it's not. Oh, thank you. Thank you. Okay, hold on. There's more if you look at the PDF. So friends who are like me and go right to the online book, this problem might just be impossible to you if you don't have the, you have to look at the PDF sometimes. Sometimes the online book, though we as a staff who created this, uh, supporting Emiliano, who works at Cascade to make this online version, we didn't catch all the mistakes. So, and not everything got translated from PDF over here. So let's go back to the PDF version. Thanks, direct messenger. I'll head that direction. PDF. Seven three. It'll be right before these chapter highlights. Hey, yeah, look at that. Chicken diet and weight. Now we can see not just the box plots, the mean, standard deviation, and the size of the little groups of chicks. And in my imagination, I can now see there are 10 cute little pink chicks who are bouncing around and happily munching up their delightful horse bean snacks. All right, cool. Okay, yeah, let's look at this. So let me I think I'll just, and I'm guessing that part B is the most crucial chunk here. That's asking us to do a significance test comparing two little chick groups. Though I think part C is interesting. We always like that. What type of error might we have committed? Explain. There's like a 2-part question there. The what type of error, there's a little process I like to do. That's good to talk through. The explain piece is another little, what do they mean? We'll talk about that. And thinking about this with different significance levels is always an interesting question. Well, it's sometimes an interesting question, so we'll just find out what happens. I'm going to take a screen grab of this and I'll put it in the class notes. Make it one bigger, two bigger. Make it a little bigger so it looks a little better. But now I gotta go down here, scoot that over that way, up that way. Shift, window, S. By the power of the keyboard command for screen capture on a Microsoft operating system. Taught to me by a Stats 243 student this quarter. Here I go. Class notes, oops. Oh. Look at it. This is going to be great. Let's. Oh, wait, what? I don't want to be strange in the notes. I want to be the editor of the notes. Just got to log into my PCC account here. Cool. I'm there. And look, there's the class notes. Ding, ding. Cool. Zoom my way down here, all the way to the bottom. Hey, great work asking questions this quarter. We have 21 pages of thoughtful discussions that we've had together. It's Tuesday, February 18th. And it's our question is difference of means, homework question 7.3. Yes. Hopefully those are good notes for the table of contents. And here we are. All right, cool. Let's make this bigger. Wander through. Well, part A, anybody feel descriptive? You've had a lot of time to stare at these box plots and just gaze upon those mean, standard deviations, and ends. Remember the general descriptors of groups when you're comparing things with, say, a box plot is comparing measures of center, right? So measures of spread, and we've got kind of the median and either the interquartile range and the range are visually there to look at in the graph. And we've also got the mean and standard deviation. And then also, like, if you notice big differences between I don't know, symmetry, because we have the box plots, but distributions of weights of chickens, just linseed and horse bean. Okay, well, both linseed and horse. I don't know if I like horse bean better or meat meal better. It's so gross sounding in my favorite possible ways. Both linseed and horse bean groups, I'm just gonna say have fairly symmetric distributions. Just to get the shape out of the way. Horse bean fed chickens weights, because I'm looking at that graph as drawing my eyes because they're the lowest weight chickens in the entire feeding, experiment here. So I'm gonna say horse bean fed chickens weights are, I'll just say generally lower. And more and somewhat more consistent. I'm just looking at the box plot. It's down below that for the linseed chickens weights, and it's a little smaller. So then linseed fed chickens weights. I'm just trying to be a role model here. But does that? And if I wanted to get more specific, I might throw in some of those numbers. The medians, difference in the medians, or the means and standard deviations. I'll just See the means and standard deviations above, right? Because they're there. I don't have to retype for numeric comparison. I'm not going to retype them. They're on the paper, right? For class. Cool. Cool. Pretty mellow. Okay. Now, part B, this is the one where they're asking us to use the tools we talked about last class. Do these data provide strong evidence that the average weights of chickens who were fed linseed and horse bean are different? Use a 5% significance level. And remember, that phrase, do these data provide strong evidence, means, dear student, you gotta do the hypothesis test. Or if you prefer, create a confidence interval that you could use to answer the question. Though, with the additional use a 5% significance level, I'm just going to stick with the hypothesis test because that's the instruction here. So let's do a hypothesis test. And we'll just do it step by step. We've got our hypotheses to write, conditions to check, calculations to do. We will definitely use GeoGebra because calculating the degrees of freedom is not a human task, unless you want to go look up a really complicated formula with me. And then we'll write our conclusion and talk about C and D. So hypotheses, I'll just write them like this. Hypotheses, step one, we got the null. We got the alternative. All right, team. Hit me. Hit me with a null. Hit me with an alternative. Either one you like. Which one pops to mind? Checking to see if the average weights of chickens who were fed linseed and horse bean are different. Ding, ding. Yeah, so not different or they're the same would be the null. No difference. Perfect. So the null, the weights, or I'll just say average weights of chickens who were fed linseed and horse bean are the same. Nice phrasing, just very clear. And yeah, nice like shorthand in the chat version, horse bean equals linseed. You could even do that one like if you want to go full on stats notation, you got the Greek letter mu for, I'm going to go HB for horse bean equals mu subscript LS for linseed. That's my style, but I like Quincy's style in the chat is great. There's no like, I don't really think there's a wrong way to get the symbols done as long as they make sense to you when you're writing them down. And somebody else might be able to pick up what they mean. And then for the alternative, I'm just going to switch that the same to be, I could either throw in a not, or I could just say are different. So, and I'll use I like that style of a not equal to. Just type a slash, in between a couple of equal symbols as role modeled by Quincy in the chat. Nice work. Okay, cool. Great hypotheses were set up for the calculations. But let's just double check the conditions for inference first, so we don't get ahead of ourselves. There are, oh, it's nice here. There are basically, well, there's two ways for the data to be independent. Data independent, both within and between the groups. That's the simplest thing to check for independence is if they've got a random sample of chicks in each group and random assignment into these feed groups. If I remember right, they did say something about random chicks. Newly hatched chicks were randomly allocated into 6 groups. Cool. So that random allocation should, randomly allocate the little chicks who are destined to become big chickens, and the little chicks who are destined to become small chickens just because of their, their chicken genetics, regardless of food, are randomly spread out through the groups. Great. Yes, random assignment makes this reasonable. And then the other one is the classic, we're working with inference about means, and we're going to use that T distribution. We want to be sure that neither group comes from a wildly skewed population. And well, looking back at the horse bean and linseed graphs, or just back at our notes, we saw they were fairly symmetric distributions. That's probably good enough there. So it's small samples, but the symmetric distributions make normal populations a fair assumption for us, and that means the math should work out great. So normal populations, yes, fairly symmetric. Support this, support this. We're in good shape, relaxing. Okay, calculations. Groovy. Let's go off to our buddy GeoGebra. It's going to be our friend, the t-test difference of means. Here we go. I'll wander off to GeoGebra Classic through the path of our D2L links, so I don't have to type anything. Hey, GeoGebra Classic, how's it going, friend? Hey, probability calculator, old buddy. Okay. Statistics side of the probability calculator for our hypothesis testing needs. In here, we're going to cruise right into the routines. T-test. T, little samples. We don't know any population standard deviations. Difference of means. Our topic at hand, two groups independent of one another. Alternative hypothesis, that was not equal to. The null is just, we're never not going to have zero for our assumption here, so just never mess with it when you're doing a difference of means t-test. It is possible to mess with it if you had a different assumption, but we won't. So, and also never mess with that pooled checkbox. There's no need to pool anything here. Just leave that be. And we'll just put in our little chicks sample one. I'm going to make sample one horse bean, I guess, or linseed. I'm going to go in the order they are in the graph. So yeah, horse bean first, just like Quincy's notes. So 160.2 is the mean of the weights of A. What's that question mark? That's annoying. Bye-bye. That works. I couldn't help but type the zero like it had in the other thing. Standard deviation, let's get that in the place to be. 38.63. And I did peek at the sample size. There's 10 chicks who ate horse bean. Let's go back and get the stats for the linseed chomping chicks. 218 and 75/100ths. That standard deviation, it's 52 and 24/100ths. And did I read that 12 right? Is it 12 little linseed chomping chicks? Yeah, okay. Just double checking the numbers are good. I think they are. And there we go. Look at that. We've got a p-value down at the bottom. Test statistic of -3. If you round it off to the 10th, it's -3 and no tenths. That complicated degrees of freedom number, it's a wild number that's bigger than the two sample sizes individually, and it's smaller than their sum. Trust me, there's a square root and a lot of other math involved in its calculation, so let's not worry too much about it. Standard error is a very similar number. Kind of cool. Let's just grab a shot of this for our notes. Looks good. Doesn't have to be a huge, massive, giant thing like that, though. Okay, cool. All right, team. Oh, okay. Yeah, good comment in the chat. For some reason, when checking my answer, the book had the p-value times 2. Okay, that's because, let's go look at this text answer together for a second. Well, it should be right here too. Okay, so see what's happening here? They left the conditions to us. That was thoughtful. Thank you. We considered them. But then their calculation, they've got their t-score of 3.02, and that's not difficult to calculate with the information given. You just need to know the means for both groups, their standard deviations and sample sizes. The t-score combines those numbers together in a thoughtful, analytical way. So they've got 3.02. Like GeoGebra, if we round ours off, it's negative, but being negative or positive has no impact in the not equal to world of alternative hypotheses. So great, that works. They just did the subtraction the other direction. Though, when we go back to this chunk of this thing here, their degrees of freedom equals minimum of 11 and 9. They're doing it the old-fashioned way. They're not using a computer for the degrees of freedom. They're using the old-fashioned way. So then with their 9 degrees of freedom, they would go into a statistical table in the back of a book or in their favorite stats book or this very stats book, and they'd look up a p-value rather than using a computer. The one they would look up is higher. It's about 1 4/10%. But wait. And the times 2 part, that would be they probably looked it up in a table that had like one tail and they'd have to multiply it by 2. Does it say that in the PDF? Is it different? I don't know. But yeah, it's because they took the other path. The person who wrote the solutions guide was guiding students through tables in the back of the book. So that's an annoying thing. It keeps happening all forever in every stats book that's a little older. Oh, we got 07. Oh, okay. Yeah, their p-value's higher just because they have this crummier degrees of freedom. They have the estimated degrees of freedom. It's a conservative estimate, which means it's gonna provide them worse evidence, a higher p-value. Now, yeah, you didn't mess up. It's just that their result is a little off because their method's different. So whenever you see like the weird little bonus notes like degrees of freedom, blah, 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 that you don't have to do it all in technology, it should be no surprise that their result is slightly different. So there you go. Yeah, Jake.
How do you know?
Oh, great question. If people didn't hear from the mic, how do we know when to do a t-test versus a z-test? Basically, in this class and in my stats life, the big thing to know is to get over to the world of z-testing, you need to be confident that, let me get my highlighter. Let's show you the difference really quick. Here's the arrow. Bam. See that symbol right there? Sigma. That is the symbol for statisticians of population standard deviation. If you know for one mean like this, or if you're talking about the difference of 2 means, z-test difference of means, see that? If you know the population standard deviations for the groups, then the z-test works. But for us, every single example we're going to see all quarter is going to give us sample standard deviation, S. So since we've got sample standard deviation S in our notes and in our work, we want to stick with a t-test.
population. But in real life, I would rarely be able to get that right. Normally, we can only say
There's, I think there's settings like quality control at, say, a factory and stuff where they kind of do have population stuff. So there are settings outside of our class, definitely, where researchers might have access to population, at least really solid estimates of population statistics. I'm sorry, population parameters like standard deviation for comparison. So the Z methods do work in those settings, but every example in our book, every time I put something on the exam, it's just like the one we're looking at right now. We're always going to be working with sample data. And oops, where's our sample data? And these SDs are sample standard deviations. They're not, it's just for these 12 chicks, those 10 chicks, those 12 chicks. So yeah, we don't have sigma, the population standard deviation. So stick with T methods unless you're confident there's a reason to switch over to Z methods. And some nerd nearby would know when it's time. Yeah, so cool. Okay, well, we got these calculations done. Now let's the last stage here. Where are we? How's my notes looking? They're looking pretty mediocre. Okay. We just got to get a little conclusion. I'm not gonna ask you all to role model for me. P is low. Null's gotta go. We have evidence of a significant difference in mean weights of chickens who are fed horse mean and linseed, right? Just significant evidence of the alternative hypothesis. Cool, relaxing. And for P is low, I can put in parentheses if I want to be classy. Our 0069 is less than the 5% significance level they talked about. So P under 5%. All right, cool. Now, part C is one that I like because this question, what type of error might we have committed and explain? It's a great question to just ask after any hypothesis test to think about as a researcher, like, okay, what if our samples are bad? What if we're wrong? What kind of error happened? And what would be the sort of impact there in the world of chicken feeding? That's the explanation piece. Let's look back down. Error type. Okay, my process is to just remember there's only two types of error. Type 1 is when you reject a null hypothesis incorrectly. So you have a good assumption, but you got an incorrect rejection. So one bad thing. Type 2 error is you did not reject a false null hypothesis. So you start with a bad assumption, doesn't get rejected. Whenever I want to talk about the error type in a specific hypothesis testing situation, I look right back at what happened. We rejected the null, right? We rejected the null. So the only error type that is possible is, careful, if we've rejected the null, the only way we're wrong is if the null was good. So a rejected null, we could have made a type 1 error. So we could have made, so only a type 1 error is possible. That null rejected would be a mistake if it was true. uh, so that would mean if indeed, if there was an error here, if there was bad data here or bad luck, we might be, we might have evidence, of a non-existent difference, right? So maybe if, I don't know, is it, which feed was the one that got them? Linseed looks like it makes the chickens a little heavier. Like, what if it doesn't? What if the horse bean, those 12, 10 chicks were just littler chicks normally, just bad luck for chick sorting randomly? And the linseed chicks were just happened to be bigger chicks, just randomly, bad luck. Um, this might be a bad result for the chicken monster farmers if I don't know, linseed's more expensive than horse bean or something, right? And the cost of, like, you'd be feeding your chickens the more expensive food, but they wouldn't be getting any fatter and more valuable to the grinding horror industry. Pardon me, to the cute Disney farm, the cute farm, where the happy farmer feeds the happy little chicks. And they cheep and they sing little songs. Yeah. So, yeah. Um, yeah, and not a difference in chicken weights due to feed. Kind of an odd thing to think through. But if those two feeds are similar in cost, it would have no impact at all. It would just be like, whatever, you're feeding the chicks different food, doesn't matter. And part D, interesting too. Would your conclusion change if we had used alpha is equal to 1/100th? Textbook got the doubly high p-value, theirs would, but not ours, because we had a stronger degrees of freedom, a better calculation. So we just say here, no, still strong evidence, still significant evidence. That alpha is 1. No, not for the textbook. And of course, there's another wrinkle. If you're working through this and checking your work, they're going to have a completely different result there. So yeah, I can see it's a good question to ask, because there's definitely some wrinkles in the technology choices. Us, modern technology, textbook, decades old, but still, I guess it's modern enough for people to still use the good old fashioned tables in the back of the book. Enough teachers out there who want to take away computers and calculators on tests. Don't know why they do that or who they are. I wish they would stop. Just stop, you weirdos. Pardon me. That's like saying I'm not going to use the internet to order my. I refuse to use the internet to order food. Who would do that? I have to call the person. If they don't talk to me, I'm not going to order from their restaurant. It's about that thoughtful to force people to use a table in the back of a book. I mean, emotion. It's not thoughtful. All right, team. Great question. Now, does that clear up that confusion for you? And hopefully just another good example of that technique for everybody. It's good to get another example of a technique that's new to us. Yeah, yeah, yeah. Mellow. Let's talk about the new technique. ANOVA. Okay, cool. A thumb up in the chat. So at least one person got something out of that discussion. Awesome. Great question. Always great. I love homework questions. Love, 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 love them. Oh, cool. And more folks have showed up. Hey, you're welcome. More folks have shown up. I see y'all in the old participants window. Welcome, welcome, welcome. I hope you're getting something out of our homework time. And now let's switch gears to our new topic, which lives. Remember, last class I mentioned this on my sickly, sorrowful morning. Now I'm just normally sorrowful from thinking about factory farming, but less sick. In any case, I reminded us last class that this new topic, ANOVA, when you want to do the reading and especially also work on your homework, things live in a different place. The topic is not in the second edition of the textbook. Like, we were just looking at the online version of our textbook. Once you're at section 7.3, The only remaining section of chapter 7 in the online book is chapter exercises. So 7.4 is just a bunch of bonus exercises. That's also true in the PDF, the fourth section of chapter 7. If you're in the second edition of our textbook, is chapter exercises. So when you want to work on these ANOVA problems or read more about ANOVA, you got to go to the first edition of the textbook. That's that 1E right there. That lives right back on our page I went to get that PDF before, back in content. Down there at text and technology. Second edition textbook's been great for us all the way up till today. But now, if you prefer the first edition of the book, if you like the PDF version for ANOVA work, pop open the first edition, read the section 7.4 to get more ideas after our discussion today, if you want to read more. And the homework problems all live in the fifth section of the chapter. Old edition collected all the problems from all the sections in one section at the end. So the ANOVA textbook homework problems all live in 7.5, whether you're in the online ebook or in the first edition of the text. I'll walk you there probably after our discussion today. Oh, wait a minute. But before we do that, did we last class when I was sickly? Did we do a little quiz about the topic we just talked about? Do you remember? No. There's this little equivalent confidence level quiz. We did talk about this concept last week, I know. Or did we do this quiz? Did we do it? Did we? Did we? I think we did. Did we? Let me just look at it one more time. Yeah, we did this. Didn't we? Didn't we? No, we didn't. I'm having like a ghost memory. Okay. Check out this question. What is the equivalent confidence level for a one-sided hypothesis test? If you choose the classic significance level, 5%. Make a drawing here. Give me my blue pen. Significance, bad drawing. Significance level 5%. That means in your hypothesis testing world, let's say we're getting a bell-shaped curve like we do for proportions or for means. That would mean if you're doing a one-sided test, you're going to have, I'm picking less than because it just was the first one that came to mind. If your test statistic, if that's 5% of the area right there, if your test statistic comes down in this range, in this lower 5% of that tail, you're going to trash your null hypothesis because the null hypothesis sets the middle of the curve. If your test stats out here, bye-bye null hypothesis. Okay, that's the significance level part of the drawing. Let's make that this color. I don't think we've talked about this in detail, so I just want to make sure you can see the picture very well. Do I have a ghost memory? I feel like we've talked about this. Am I having deja vu? Ah. Oh, we did talk about it. On the slides. Okay. I see. Talked about it on the slides. All right. I'm not wild. We just didn't do this quiz version. Okay. But remember, so this drawing, we could even do this drawing all on this one curve. The idea here is a confidence level. If you want to have an equivalent confidence level, give me a green pen for confidence. I want to be confident. Every time you want a confidence level, you want to shade in the middle chunk of your distribution. So to get an equivalent confidence level, I'd go from, leave that 5% tail there, and I'd color all the way up this way. I'd leave another 5% tail over there and just color in the middle. This would be, trying to color. That's really, really artistic coloring. Beautiful. It's not as beautiful as the little horse I drew yesterday in Stats 1, but it's pretty great coloring. I drew a little horse, it was pretty good. But this drawing isn't symmetric because I wish it was, but let me just, a couple more details. If I go chop that off on that side, this would be the other side, the other tail's got to also have 5% to get the confidence level. Confidence level's got to be centered there. So this should be our confidence level right here. See that? Is my drawing clear enough now? If that's centered, if that were centered, get rid of that little weird little mark. Pretend that's centered. And that's the middle area. So it's got to have the same 5% in each tail. That leaves for us in the center. Did I get you there? The number? It's what? Yeah, 90, exactly. So that's gonna be 90, because if the other two, if the one tail that's the significance level is 5, you got to think of 2, so double it up. And your good old confidence interval, there you go, confidence level there, that's gonna be 90 right here. And that, our friend, our world, it's that 90. Check that and ignore the other 3 options. They're just there to distract and confuse you. It's multiple choice. Multiple choices are designed to distract and confuse you. That's what they're for. And even 2 of them are just a complete waste of your time. The only one that's distracting is the 95% option. That one, sometimes people are drawn to just, oh, shouldn't they just be a subtraction from 100%? And in the case of two-tailed hypothesis testing, that does work, because then your significance levels in both the tails. But here, one tail, so you got to double that significance level, take it away from 100 to stay in the center of the confidence level, like that. All right, cool. Get that point. Be sure to check this box and then submit your quiz to get your point, and we'll and then, oh, and we're at a perfect spot. It's 10 till right now. Let's take a break, and we'll totally shift gears ANOVA time right after the break. Sound cool? I hope so. See ya after the break. Which will end at a minute past the hour. 4 more minutes of break. Oh, I'm gonna look at my phone. Ugh. No, I'm gonna do something on the internet. Up here. Typing. Oh, good question in the chat a minute before break ends. Did my kid get to play in the snow? Oh, only a tiny, tiny bit, because Thursday and Thursday, okay, at the end of our class, like I think even like before we stopped talking, I got a text from my co-parent that said something like, I can't move or something like that. Like she got sick levels worse than me and my kids, so and I was still feeling bad that day. So I ended up with my kid on his snow day, Thursday, and his other snow day, Friday, but I was still sick and she was sick, both of us too sick to like get out in the snow and play. A couple of his friends did start to make a snow fort, I think, on like Saturday or something, and he got to get out there and mess around a little bit because I was starting to bounce back and maybe he was just running back and forth between the houses because we live real close together, but he did, but not as much as he should have. I'll put it that way. Supposedly, I owe him now. I owe him a significant amount of fun because he was denied the true joy of snow days. It sucked. Yeah, it sucked to be sick on days when your kid wants to get out and play. Like, yeah, he didn't go to the park. He didn't go to the park. That's bad on the snow day because two parents, one couldn't move at all, his mom, and the other one was just a sniffly, fever-ridden, gross me. But yeah, but he saw the snow through the window, and he did get out and play and see some friends who made a snow fort. Although I can tell you, there's some snow fort controversy. And some friends got a little upset with one another. And I have no clue what happened, but hopefully they'll work it out as kids. Okay, team, we're back. We took a quiz. We talked about more about difference in means hypothesis testing. That's a good talk. I'm glad we got more into that topic. And now let's talk about our new topic. It's called analysis of variance, or for short, ANOVA. Here we go. Let's use the slides for the discussion. Comparing means with ANOVA, see, they're just 7.4. Just another slideshow. It's kind of an interesting, I think it's this is an interesting topic for sure. And I think this example is actually a kind of a cool, interesting example. So, oh wait, I got a tea bag to get rid of. I'll be right back. I'm almost back. And I'm back. Okay. N short for analysis, O short for of, VA short for variance. Comparing means, we just did that in the previous section for two independent groups. The ANOVA technique does that for more than two groups. So the math is and the analysis are much more complicated. We'll get into some of the details of how it works, like a peek under the hood. But this is another one where it's impossible to do these calculations by hand. You've got to depend on information being right there in the textbook for you, or using technology to do these calculations. There's just stuff that you just wouldn't want to try with if you didn't have like a team of nerds with you to double check your work. And that's actually how it got done in the olden days. Teams of people. We have a cool example to drive the discussion. This is a map of the Wolf River's drainage basin. You can see it spreads across the border of Tennessee and Mississippi. The floodplain is shaded in blue, so when that river swells up, it could get pretty big. You can see it goes from good old Memphis, Tennessee, a wonderful place to go to listen to music and hang out with some music lovers and do a little anti-racist activism while you're at it. And all along the river, there's all these smaller towns in Tennessee, all the way up into Ashland, Mississippi. So there you go. Beautiful. Oh, maybe it's not completely beautiful. This river flows past an abandoned site once used by the pesticide industry for dumping waste. What's called by economics experts externalities. If you're making a dangerous chemical and there's a bunch of waste products that you can't sell, well, the most economical thing to do is dump them in the nearest river. Fuck it, kill all the people nearby. I mean, pardon me. Don't worry so much about that because you want to make money. Now, the wastes include things like chlordane, a pesticide, aldrin, and dieldrin or dieldrin, which are incesticides. And I could be mispronouncing any of or all three of those asides. These are all highly toxic organic compounds. They can cause cancer, birth defects, and I'm sure other bad health outcomes for people. And I'm certain it's true for other forms of life as well. The standard methods to test whether these substances are present in a river is to take samples at 6/10 the depth. So, think of the surface of a river, the riverbed, and 6/10 depth, full depth would be the riverbed at the bottom under all the water. 6/10 depths would be just a little below, halfway between the surface and the bottom of a river. And that's where fish are swimming. If the river is shallow, there might be people, swimming down there and playing. If you're a person fishing for fish, the fish are going to be fishing through that level, even if you're fishing for bottom feeding fish, like yummy, yummy catfish. Okay. Since the compounds, these dangerous chemicals, are denser than water, and their molecules tend to stick to particles of sediment, they're more likely to be found in higher concentrations near the bottom than near mid-depth. Okay, wait, wow. So if I'm fishing for catfish who are bottom feeders, because I'm a southerner, they like catfish, yikes, that's exactly the worst place to be fishing, because that's where the most dangerous chemicals are in the river. Bummer. Okay, so some researchers wanted to double check if mid-depth really is the best, place to be taking these measurements. So they got a data set here of, well, it's aldrin concentration in nanograms per liter. They took, you can see samples 1 through 10. So the first 10 of their samples were taken at the bottom of the river for aldrin concentration. They took 10 more samples, samples 11 through 20 here at mid-depth, the traditional depth. And then they took 10 more samples 21 through 30 here up at the surface level. And so 10 measurements at each depth. Okay, the idea being, yeah, is it similar enough? So if we're concerned about safety on the surface, like where children might swim, does measuring at mid-depth, is that good enough to know if it's going to be dangerous up at the top? And if you're concerned about bottom feeding fish and stuff like that, is mid-depth good, compared to the bottom? Are we going to miss something? Interesting questions, and you want to just check and see, are the mean aldrin concentrations similar at these three depths or significantly different? Okay. We can look at the picture in more detail. There's a dot plot with all 30 measurements at all three depths. Got to sip this tea while it's just the right temperature. Graphic design wise, I got to say, you got that backwards. The surface measurements here are in the bottom of the graph, so I'm kind of visually, I wish I could flip those. But you can see that the lowest aldrin concentrations in their data set are at the surface, from just more than 3 up to just more than 5 nanograms per liter. At mid-depth, starts out just slightly higher for the minimum mid-depth measurement, but they go way up to 6.5 nanograms per liter. So they're more spread out and they're generally higher at mid-depth. And then at the bottom, the lowest measurement's closer to 4 than 3, and they spread all the way out up to 9 nanograms per liter. So, more spread as you go deeper into the river in the measurements, and they tend to be higher as well. You can see the differences in the means down there at the bottom. About a nanogram per liter greater from depth to depth. And standard deviations, well, they get a little bigger, from group to group. It's hard to tell because the scale, like, those numbers are different, but I'm not really sure how different a nanogram per liter feels to a researcher concerned about aldrin concentrations. I don't have the scientific or health knowledge to know where these numbers become concerning to me and stuff like that. I'd have to read more. So I wish they were all 0. I wish we could. I wish all of the sons and daughters and children of those wealthy, murderous pesticide manufacturers would have all their money taken away for healthcare. Seems fair. And all that blood money could be spent to keep people safe. Hey, clean up the river. A good idea. Just thinking out loud. Good old obeying the law. Love it. All right. Research question. Is there a significant difference between the mean aldrin concentrations among the 3 levels? Great question, because if the answer is no, then yeah, you can just always measure at mid-depth and you're going to get a pretty good sense of what's going on in the whole river. If the answer is yes, then you might want to change your measurement practices depending on your health and safety concerns. Yeah, great research question. And here come the notes about things getting complicated statistically, because now instead of having 2 groups to compare, like those 2 groups of chicks who ate those 2 kinds of feed that we talked about before the break, now we've got 3 groups, 3 levels to compare. When we compared the means of 2 groups, we use I crossed out Z because we never have that population standard deviation. We use the T distribution like before to perform a hypothesis test or estimate a difference using a confidence interval. Okay, cool. To compare means of 3 or more groups, like here, researchers perform a hypothesis test called ANOVA, analysis of variance, which uses another model called the F distribution, a different probability model. So like when we met the chi-squared distribution back in the chapter on categorical data analysis inference techniques, we're going to meet another curve here and look at some of its interesting features along the way as we work through this example. And we'll look at it in even more detail next class. So this is like a two section discussion because there's a lot of math details that are under the hood here to look at. And yeah, it's a lot. So just, be patient, ask every question, and remember that technology will be our friend when we need it in a lot of this work. Okay, ANOVA is used to assess whether the mean of the outcome variable is different for k categories of a categorical variable. So here we've got 3 depths. Our categorical variable is depth, and our 3 categories are surface, mid-depth, and bottom. 3 is our k. Null hypothesis in the world of ANOVA is always the same. Assume the mean is the same for all the categories we're looking at. So assume the same aldrin concentration at all river depths on average, same mean concentration at all depths. The list of means can get as big as you like. And then the alternative hypothesis is just the means are not all the same. So at least one would be different enough from the others to pick up analytically, to see as a significant difference. Or they could all vary, and it would pick that up if it's enough variation to seem significant analytically. Okay, so at least one mean different than the others, or heck, all of them being different, but could be any combination. The test won't tell us which one's different and how, or if it's more than one being different from each other. It just tells us things are not different, or sorry, it just gives us evidence of some difference. Conditions, of course, once we've got a new hypothesis test, and especially when we find a new distribution name, so the F distribution's a new probability model, it's going to have different conditions than the normal distribution, the chi-square distribution, and the student t distribution. It's just a different probability model. One of them is familiar. We just talked about this before the break when we're looking at 2 groups. Observations should be independent within and between the groups. That's just our normal universal assumption. We need independent data. The normal thing to check is if you've got random sampling and you're in good shape. There's that less than 10% of the population. That's actually, never be bound by limiting sample size. Bigger samples are better. It's just that when you go past 10% of a population, there's some mathematical correction to do that bigger nerds than I understand how to do. You'll never have to worry about that in detail. Just considering whether the data is independent or not is crucial. So just there should be no pairing, no grouping, no relationships among any of the data values. Random sampling or random assignment or both are the best. Now here, they don't care about the sample size kind of at all. They just want the observations within each group to be nearly normal, or at least that it's safe to assume they might be. And interestingly, this gets, just like with the other means techniques, more important the smaller the sample sizes get. Although it's also kind of harder to see on a graph if things should be expected to be normal, bell curved, the smaller the group gets. So there's a little tension there in what to do. So how do we check for normality? Well, we have a few methods we'll talk about as we go. And then variability across the groups should be about equal. And I'll be honest, I've only read about ANOVA because I'm not a statistics major from college. I majored in math. I've never read in an introductory stats book because I've, read, I don't know, however many I've read to try to learn to teach this class better, but none of them explain what about equal, like what that means. They just say it and then assume that they're all good enough for the homework problems they give you. So I'm not exactly sure how to check this condition beyond saying, I guess they're similar for every single homework problem. So they don't really give us many clues in introductory stats books, and I've never read anything anywhere that made it clear at my level of learning what about how much wiggle there is there. So let's check these conditions in the slides style for our example. Independence, those river depth measurements, should they be independent of one another? Let's see. They're saying in this study, we have no reason to believe that the aldrin concentration measurements won't be independent of one another. I've got to come back. I also have no reason to believe that they wouldn't be dependent. They didn't describe at all in any way how or where on the river as far as, if you dip down your thing into the exact same river location 10 times in a row and take 10 samples, that's going to be terrible. But if the research team are thoughtful and careful, and they, spread out their sampling at the different depths around the river at different times of the day throughout a certain, do some randomness in that process, not hard to figure out a way to make independent, randomize your sampling enough to make it independent. So, okay, I'm with you. Let's call it independent. Let's trust our researchers did their best, and somebody on the team was like, we got to randomize our sampling so that we'll have good data for statistics. Let's trust it. Oh, the approximately normal one with 10 measurements at each depth. First, look down at the histograms for the measurements. Like if I put those histograms on your exam in Stats 1 and asked you to describe their modality and their symmetry, where's my noodle? Give me my little noodle. You like pesto, everybody? Pesto? People on their Stats 1 test would say this is a bimodal distribution. It does not look normal. They'd say this one is, well, that's 1 and 2, right? So is it uniform? I mean, is that even really a mode? Is that even I don't know. This one, maybe somebody might say they could imagine a normal curve over, but it's still just, if those were dots, like a dot plot, instead of histogram blocks, I'd be even less convinced that a normal curve might fit over those graphs. Now, do people remember this funky looking graph from Stats 1 at all? We only looked at it for minutes in my classes, or because it doesn't come up much in Stats 1. That's called a normal quantile plot. See this line here is like a line that shows on the scale of the data set how things compare to like what would be a normal distribution. So when the little dots in these plots, oh, that's hard to see the dots, sorry. Give me my eraser. Oh, all my drawings go away. When the little dots here are close to that line on that graph, fairly close, and they look random, just randomly spread around on either side of that line, the mid-depth graph is the best looking one. See this one? Little dots are all fairly near the line and scattered on either side in a random way. That's a really safe to assume that could be a normal distribution, because the variation away from, if it is truly a normal distribution, they'd be right on the line. So that looks great. Bottom depth, maybe there's like a little bit of a pattern to those dots, and the more of a pattern you see, the more skewness is evidenced. And we did have that funky little bump with 2 higher measurements there in that last category. But they're all still close to the line, dang close. So And is that a pattern or is it just because there's only 10 dots, you know? It's hard to tell. And the surface level, a couple of little dots are not so close to the line and they're kind of grouped together, and that's not the best thing because of the gaps and stuff. But at least all but two of them are dang close to the line and they're fairly parallel. I'm going to go give it a check. So if those graphs, these normal quantile plots, do have generally close to the line, generally random spread around it, that's the best check for normal populations we know how to do when we've got like a small data set. We're not going to mess with GeoGebra this class to do this, but we will next class. So next class we'll have data sets to play with and like do all go through this test with like a calculator and walk through it that way. But this class, we're just going to focus on how that works first because it's complicated. All right. But so I'll make sure to remind you how this works next class with technology. You can make that graph if you want. Constant variance, here's the thing. Does this condition appear to be satisfied? Well, if I don't even look at the scale, I would say no. The first graph is way more spread out than the third graph. But then if I look down at the numbers for standard deviation, they don't even differ by 1 nanogram per liter. But is a difference of nearly 1 nanogram meaningful? Like, I don't know. So again, this is one where I've got to, only one of my friends who works here and teaches stats was like he's like he has like a doctoral degree, I think in like computer science or data science with a minor in statistical, stuff. So he knows statistics. Maybe he's the guy. I should ask Ari. And he can maybe explain. I mean, I always just check this one off because I think, why would you put it in the book? If these are too far from each other, why would we be using this for the example? So I don't know how to convince myself of that one though. So if you feel not sure on the constant variance thing, still just go ahead and do your hypothesis test is what I'm saying. But if you do notice a big difference in the spreads, you'd want to note it in your work. Okay, bonus reminder. In the world of comparing means from two groups, like before the break today or like last week, we want to check to see whether those means are so far apart the observed difference cannot reasonably be attributed to sampling variability. Null hypothesis assumption, mean 1, mu1, is equal to mean 2, mu2, mu2, mu2. Scary. ANOVA, this is our new situation, comparing the means from 3 or more groups to see whether they are so far apart that the observed differences cannot all reasonably be attributed to sampling variability. Long sentence, but just assume for your null hypothesis that the mean values mu1, mu2, all the way up to mu, however many groups k you've got, are all the same. Oh, mu2. You were so tough that first time I fought you. I was like, whoa, this is so powerful, this guy. I'm never gonna catch this guy. Gotta get that master ball. But then I became a more powerful Pokemon trainer. And by powerful, I mean I was willing to throw 1 million regular Pokeballs at Mew just to see if I could catch him with one. If I knocked him down to like 1 hit point, I could. Just had to throw Pokeballs all day. All right. Here's where it gets still more complicated conceptually and analytically. Okay. Last week, when we talked about computing the test statistic for the t-test, well, the t-statistic, so let me just, we're not talking about z-tests, we're talking about t-tests. I really should just edit this slide sometime. the T statistic, just T. We had our difference in sample means. That was from the data set. We'd subtract away the assumed difference, which we always assumed was 0. So that was an easy subtraction. And then do division by the standard error, which estimates how that difference in means would vary if we had different samples. And it just had a formula that related the standard deviations and the sample sizes of both groups. There was some addition and some squaring and a square root and some division. It was a little formula. Not hard to just, if you've got those statistics, quickly calculate the test statistic. Okay, now this, in the ANOVA world, the test statistic is again a ratio. So there's going to be a numerator and a denominator. But the shorthand is wild. F, that's the name of the test statistic. Oh, and it's short for Fisher, the last name of a horrible man who was also a very, very influential statistician. And by horrible, I mean a Nazi sympathizer. Really bad, super bad. But variability between groups and variability within groups, what do those phrases even mean? They sound so similar and they're so strange. Slide maker, what did you do to help me? Let me just check. Is there a picture? No. And then they're saying large test statistics give us small p-values. So when the ratio gets you a big number, you'll get a small p-value. That's just a little mystery right now for us. If the p-value is small enough, well, we'll reject the null and have evidence the means are different. That's normal, that last sentence, but variability between groups and variability within groups. Let me go back to the box plots of the data set and show you what they mean there. What was our best graph? Not that one, I don't think. Those aren't the good graphs. I think our best graph was the one that showed the picture. Oh, is that the best one? Oh, I think the box plots are the best one. Okay, let's go look at those box plots for a second. I did just peek back at the means of these three groups because those are the medians on the box plots. Let me draw in the mean values of these three groups. I'm just going to use an orange pen for mean values, okay? It was about 6 for this group. It was about 5 for this group. So the mean and median are very similar there. And for the surface group, it was about, I saw it, it was 420. I don't know anything about 420. Something like that. So those are the mean values. Remember, what we're trying to figure out is there a significant difference between those three values, the means for these groups? The between groups variation, what they mean is the variation of the means between the groups. So think of, let me get some arrows. This mean is about that much higher than that mean. See, from the bottom group to the mid-depth group. The mid-depth group's mean is about that much greater than the surface group's mean. And if I start at the surface group's 420 and go up to the bottom depths 6, see that? Those little orange arrows, those are the visual representation of the variation between the groups. By that, variation in means between the groups. Did I get that right? Let me look again. Yeah, between the groups. Okay. Now, the other one's variation within the groups. And that just means what it says, like if I look at the bottom dwellers there, their standard deviation is 158. So if I want to, 158 for 110 for the mid depth or 66 for the surface. If I go, I don't know, I'm not going to try to draw standard deviations. I'm just going to look at the dang boxes, right? A little further than the box will get you about a standard deviation in both directions, give or take. So those green arrows, just, the variation you see in the box plots is the variation within the groups, right? Now, what Fisher, the horrific man, analyzed thoughtfully, if you're assuming the groups all have the same mean, well then, of course, there's going to be variation in the means between the groups just because of randomness. But the more variation there is between the groups in comparison to how much things are varying generally within the groups, the more evidence you have of a genuine difference in the means. We'll draw some more little boxes as we go, but that's the big idea. So the between groups, that's between the means, and within groups is the variation you see in all the graphs you're looking at. Okay, whew. Complicated ideas. Took me a while to even understand what they're talking about when I was reading these ANOVA sections in different stats books. So I'm sure when I say it out loud now, it makes sense to about, I don't know, 0 of you or 2 of you, or but if it makes any sense at all or feels like there's an idea there that is clicking, then great, because it really is wild. Variation between the groups is variation of their means. I wish they just put it that way. And variability within the groups, I wish they would have called it the group's standard deviations or the group's interquartile ranges. If they would have given it more of a name that resonates with the stats we know, maybe it would have been easier for us to discuss and learn this topic, especially when stats are newer to us. But let's see some more details here. For our example now, we're not going to go into any details at this moment about how the F statistic gets calculated. Let's focus on some other details of what's up. First step for hypothesis testing is to just write out our hypotheses. Can we see, based on our few slides discussion here today, which of these is going to be the best looking pair of... This is not a really fair multiple choice question. This is brand new. Oh, maybe it is fair. Yeah, I'm with y'all. C. We don't want to do any specifying in the alternative hypothesis about like no directions. We don't want any directions like that. We don't want to say that none of the means are equal to each other, because that's too much specificity. The B is just, no, we can't have not equal to in the null. But yeah, assume all the means are the same at bottom, mid depth, and the surface. And then alternatively, let's see if there's evidence that at least one differs significantly from the other. Okay. Pretty relaxing. When you're in ANOVA, the null hypothesis writes itself. Assume the means are equal. That's simple. There's a picture of the F distribution. Idea is you go up this scale in this picture when the means vary more than you would expect compared to how the values vary in each group. Tricky sentence. We can look at this curve in GeoGebra as well. I'll head back to the distribution side. I think it's like the 4th one on our list. Yeah, student, chi-squared, and F distribution. This is our last new one we're going to meet this quarter. Just so, sorry, exponential and Cauchy. You're for other people in different classes, in different walks of life. But there's our F distribution. We're always going to we're going to get the statistic, and we're always going to get a p-value by looking at the right tail, kind of like chi-square. It's this funky looking skewed thing. So we're always going to look off at that long tail. And notice that instead of having 1 degree of freedom to draw the funky curve, like chi-square did, it's got 2. So there's definitely more complications to figure out to get this thing to work for us. But yeah, to get a small p-value, the variation in the means, or the variability between the groups, needs to be bigger than you would expect when you compare it to the variability you see within the groups. That's thoughtful idea there, you horrible monster, Ronald Fisher, who I'd love to go back in time and punch right in the face. And I don't care if you were nice to your cousin or not. Neo-Nazi piece of proto-Nazi and Nazi sympathizer. Bad man, bad man. In order to obtain a large F statistic, see that the variability between sample means, and then this phrase needs to be greater than the variability within sample means. Bad writing, statisticians. Greater than the variability you just expect among these groups. Ugh. Within sample means. What a weird phrase I don't understand. Did Fisher come up with it? It would make sense because he's a jerk. Okay, now here's a peek at how the calculations look when they're all done. And these next couple slides, we have about 10 minutes left. We're going to kind of look under the hood of the output of ANOVA calculations. Historically, just so you know, this table at the top, it's called an ANOVA table. And it was developed by statisticians back before computers existed, when these wildly complicated calculations happen in that it's called sum of squares for short. That column, those calculations are really complicated. The other columns, they're not that complicated, but this is just how they set it up to be able to work as teams and generate these numbers together and double and triple check their work. Okay, group, that top row, that is the, if we're gonna use my colors, the groups are the means. So the group row focuses on the variability between the means, between groups. The error row, that is the row that focuses on the variation within the groups. Annoyingly, those two might be labeled differently in different settings. Like you can see right here, it's got a label residuals instead of error. You'll see different labels in different stats books. They're not universal. Depth, though, you'll often see the name of the categorical variable right there for the groups, because they are the groups. So cool. Depth. All right. Now, degrees of freedom, to draw this curve correctly, the degrees of freedom have to be calculated. There's 2 versions. The first row gives us degrees of freedom 1, so that 2 is just 1 less than our number of groups. So degrees of freedom for the groups, G, 1 less than number of groups, we get 2. And then the residuals one is you take your total number of observations, we had 30 measurements, and subtract your number of groups. Okay, that's 27, so that's that one. And the total row, that's the bottom row. Well, that's your total number of observations minus 1. And notice the degrees of freedom all add up together. 2 plus 27 gives you 29. Beautiful. Lovely little relationship there. And now 2 and 27, those are the official numbers that will get us the actual curve that computers are going to use to compute a p-value for this setting. It won't have that hump. It'll just be fully skewed off to the right. Okay. And now, just so you know, in your homework, our textbook's going to just, give you some of these tables like this, and they might like leave 1 or 2 of these blank. And then you could either come back to this slide or look in the text in the chapter to, double check the formula or remember how things add up and get the numbers together. So that's just a little homework problem they give you to kind of play with and understand how the table works. Okay, Let's look at the other more complicated column before class gets out. Oh, there's the calculations. I wish I'd lit that up before. There they are in living detail. Okay. Hey, look at these formulas here. You don't want to try to even write that in your notes because it's just something you're never going to do by hand. Sum of squares calculations are things we use computers and spreadsheets for. The sum of squares for the groups, that's 16 and 96 hundredths there. That's to measure the variability between the means in some analytical way. It is interesting how they do it. Let me just use a highlighter to talk about it. Each group, so X bar subscript I, that is, well, so X with the bar 1 would be the first group's sample mean, X with the bar 2, second group's sample mean. You take those numbers and you subtract away from them just X with a bar, which is the mean of all of the values in the entire data set. So it shows you like those differences give us, well, how far are the individual groups' means from the whole mean for everyone? If the null hypothesis is in fact true, they should be pretty close, right? Just some random variation. The further off they get, the more evidence we should have against the null hypothesis. Statisticians like to square differences, so that happens in the formula, and the sample sizes don't have to be the same. So for each group, the squared difference here is weighted by the sample size. You add up those numbers and get this sum of squares for the groups. Some sense of how far off are the individual groups' means from the mean you would expect if they all matched. Okay. Mellow. I mean, medium mellow. And calculating that here, see that? 604 is the bottom depth. 5.1 is the total mean for all the groups. Some little formula work. Add it together with for the mid-depth measurement and the surface measurements means you get sum of squares for the groups, but I do not expect anybody to be writing out something like that anywhere in their notes, unless you're really feeling analytical and you want to get into how these numbers work. With one of these very small data sets, they're not that bad to work through, but it's just not unless you're into it's like doing push-ups, but with, arithmetic. Okay, sum of squares total, they're switching to that bottom row, this big number, 54 and 29 hundredths. Let's look at the formula with some context here. What this number is it's the variability across all the observations in the data set. It really is just, it's like the variance of the entire group. That's the squared standard deviation. So you just take each value. I'll say that's just one value, like the first observation. N would be here 30. That's all 30 observations in the data set. So 3.8 is one of the measurements. 4.8 is the next measurement, etc. And 5.2 is the last measurement in the data set. From each measurement, subtract the mean of them all, which is 5 1/10. Subtract that away, square them all, and add them all up, and you've got, that's the variance of the entire group, or the sum of squares total, as it's called in this setting. It's the square of the standard deviation of all the values, but it's how much variation you see all through the data set. Okay. And I think our slides for the number in the middle, that 37 and 33 hundredths, if you just squint, you can see the sum there, 1696 plus 3733, it is 5429. So once you get this thing all added up, if you just want to quickly get to the sum of squares for the error row, you can just do a little subtraction with the numbers you started with and come up with that value. Though there is complicated formula for that calculation. And back in the olden days, to get 33 and 3300s, statisticians would use the complicated formula. And then what they would do is double check that there are three complicated things they did. Check that you could just add up your first two complicated calculation results and that you would get your third complicated calculation result from that simple addition check. That's one of the reasons this is set up this way. Okay, once you've got the sums of squares, we only have 3 minutes left. This is good timing. The mean square column, no big deal. You just divide the sum of squares, the complicated calculation, by the degrees of freedom from the same row. So you can see mean squares for the group, just the sum of squares value 1696 divided by 2 gets you 848. Mean square for the error row, 37 and 3300ths, divide the degrees of freedom 27, you get 138. The closer together those two numbers are, the lower the F statistic's going to get, because the F statistic is just their ratio. Take the 848, divide it by the 138. So the mean squares, you can just think of you can just imagine a fraction bar right there and an equality symbol to point you over to the 614. The bigger this number gets, the lower your p-value gets, okay? And rather than give you this number and then make you go look up the p-value in a table in the back of the book, you get this number here, and there's the p-value right there waiting for you. So if I go put 6 and 1400ths over here into this picture in GeoGebra, 6 and 1400ths, there you go, 0063. There's that p-value, and you can see it's that statistic, that test stat is way out there, just at the edge of the page, but there's still, a little more than half of a percentage of the area under that curve, as you go all the way off in that direction. Kind of wild. Okay, whew. Whew. Hey, Nova, so much complicated stuff here. Oh, there's our picture of the p-value that I saved for the slides. And then they're saying, hey, look, great. There's also, they're just showing the p-value calculation, some notes, their style. We've already talked about that and set up the degrees of freedom in GeoGebra, got the thing calculated. And then when you have a very, very low p-value, the data provide convincing evidence that average aldrin concentration is alternative hypothesis, different for at least one group, right? Yeah. So lots of details here, lots and lots of details. But just to remember that the main, if we look back at this, you'll find when you peek into the homework, let me just show you quickly before you all leave. It's 10 till, we got to get out of here. But as you get into the homework, they're going to give you some of these tables, and they're just going to blank out like a few of these. Let me just grab my box drawing tool. Like they might leave all of the degrees of freedom blank because there's really straightforward formulas to get those calculated quickly when you know sample sizes and group sizes. They might blank out any one of the three of the sums of squares because you can use addition or subtraction to get one of the three. They might blank out one or both of the mean squares because straightforward division of the previous two columns gets you those numbers. Same with F. They may or may not blank out P, but they probably won't. But just, when you get into the homework, you're going to find some of these tables with a lot of blanks. If sorting out these formulas and relationships feels even a little complicated, if you're working on that early this week, bring that question to class. We'll talk about a lot more details next class, including how some of these formulas work. And of course, I'll show you how to use GeoGebra to produce this table when you've got a data set. So you'll be able to get these done quickly and accurately in regular life if you need to with technology. But this was your peek at like the engine that drives this very complicated technique. just a peek, but there'll be more peeking tomorrow. So, but at least we got through the hypothesis test chunk, and there's more topics the next day. Sorry, not tomorrow, Thursday. All right, sorry to keep you for 2 minutes extra. Have a mellow afternoon and remaining morning.